so you are welcome. Today our discussion is on electric current, resistance and resistivity. Electric current deals with moving charges. So when a conductor carries current, it means that the electrons in the conductor are moving through it. So when the charges in the conductor are moving, they are mobile. It creates current to flow through the conductor. So this movement establishes a potential difference between the points along the conductor. And the potential difference is the work done to move a charge from one point to another. So when the charges are moving from one point in the conductor to another, electric current is created. And that movement also creates a potential difference in the conductor. And this potential difference is due to the work done from moving the charge from one point to another. Now the potential difference now creates an electric field within the conductor, which then drives the continual movement of the charges. So after the potential difference is established in the conductor, an electric field is also created. And this electric field created helps to drive the continual movement of the charges, helping to hold up the current flow in the conductor. Now, electric current is then the flow of charges or the rate of flow of charges through a region of space. It's the rate of flow of charges through a region of space, and its SI unit is ampere. Its SI unit is ampere. So 1 ampere of a current equivalent to 1 coulomb of charges across a certain area in 1 second interval. So for a time of 1 second, and we have 1 coulomb of charges passing through across a certain area of a conductor, a 1 ampere of current is created. Now, the direction of current. The flow of current in the conductor is opposite to the direction of the flow of electrons in the conductor. So if the electrons are moving in the right direction, the current will be moving in the left direction. So as you can see in the diagram here, the electrons in the diagram are moving in the right direction and the current is moving in the left direction. So always the charges or the electrons and the current move in opposite direction. But current flows in the same direction as the direction of positive charges in the conductor. So the positive charges in the conductor move in the same direction as the current. They move in the same direction as the current. Now, the direction of the current in the circuit is from the positive terminal to the negative terminal of a battery. So if an external voltage source is supplied to the circuit, the current then moves from the positive terminal of the voltage source through the circuit to the negative terminal of the voltage source. So we take note of that too. Assuming that charges are moving perpendicular to the surface of area A. Now, if K is the amount of charges that passes through the area in time t, then we can therefore find the average current within that area. So the average current is therefore calculated as the charges per the change in time. So the number of charges passing through that area divided by the rate of time at which the charges are moving. That gives us the average current in that conductor. So if the rate at which the charges flow varies with time, then the instantaneous current can be found as, so we can also find instantaneous current. So the changes in current flow within the conductor varies with time. When it varies with time, then we can get instantaneous current. So that gives us the dk over dt, infinitesimal change, or the change in charge over the change in time gives the instantaneous current. Now, current and drift speed. So when electric current is applied to a conductor, the charged particles move through the conductor of a cross-sectional area A. The total number of charges carries equals n times A times change in x, where n is the number of charges per unit volume. A is the area, then change in x is the length of the conductor. Now the total charge is then given by change in Q equals n times A times change in x times Q. So Q is therefore the charge in the conductor, n is the number of charge carriers, then A is the area of the conductor. So we can therefore get our drift current, which is the speed at which the charge carriers move, to be as Vd equals change in x over change in t. So this is a normal velocity distance time equation. So we have V equals change in x over change in t, which Vd denotes the drift current. Now, if the carriers move with a constant average speed, if the charge carriers are moving with a constant average speed, the distance they move in time is given as change in x equals Vd change in t. So over here, we are just making a change in subject here, making the delta t or change in t the subject of the previous equation we just saw. So therefore, our total charge of the conductor becomes N times A times Vd times change in t times Q. So this becomes our total charge of the conductor. Therefore, now our average current, which was previously equals change in Q over change in t, therefore becomes N times A times Vd times Q. So we substitute our change in Q, which we had to be this, into this equation. So after the substitution, the change in t will cancel this change in t, leaving us with this equation. So we take note of the equation 2. Now after that, drift current then becomes, so from this equation, we make the drift current the subject of the equation. So it becomes I over N times Q times A. So drift current becomes current over number of charge carriers times the charge times the area of the conductor. So motion of charge carriers in a conductor. In a conductor, the charge carrier's motion is in a zigzag form, and this makes the net drift speed small. So the sharp changes in the direction are due to collisions of the charges with each other. So the net motion of the electrons is opposite to the direction of the electric field. So the charges moving in the conductor is in a zigzag motion form, and this is due to intercollisions with each other. And in spite of the collisions, the charge carriers slowly move along the conductor with a drift current. So no matter how they collide with each other, their drift current is contained, meaning they still have a drift current at which they move through the conductor. So there will be still collisions with each other, but there still exists a drift current at which the charges move in the conductor. So if you look at the second diagram here, their movement is not as straight as we assume it to be, but they collide with each other because they all have kinetic energy and they are trying to move at a certain speed. So since they are free and they are not guided or guarded by any electric field, they move in any manner as they want, and this causes the zigzag motion that we can see here. And this motion is due to their collision. They collide with each other and they do not move in a pattern or in the field at which they are found in. So we take note of this too. Now, current density. Current density of a conductor is the current per unit area. It is the current per unit area. So if we take a conductor of area A, the current that is flowing through the area per the area of the conductor gives the current density. So mathematically, we have J to be equal to I over A. But we know I to be equal to N times A times Vd times Q. So after substituting I into this equation, we're having J to be equal to N times Vd times Q. We're having J to be equal to N times Vd times Q. And the SI unit for current density is ampere times meter squared. Ampere times meter squared. Now, conductivity. A current density and an electric field are established in the conductor whenever a potential difference is maintained across the conductor, and the current density is always proportional to the electric field created. And within that proportionality, the constant that we take into consideration here is conductivity. So when there's current density and there's an electric field being established in the conductor, we say that the conductor is able to conduct. That's why it's a conductor. So if you have a material that has carrier density, and electric field present, we see that the material is conductive. Therefore, the proportionality constant here that we take into consideration is conductivity. So when we express this mathematically, we are having current density to be equal to conductivity times electric current. We are having current density to be equal to conductivity times electric current. So as you can see here, when current density is proportional to the electric field, the constant to take into consideration here is conductivity. So any material which is conductive has electric current and electric field present. Now, Ohm's law. Ohm's law states that the potential difference applied across a conductor is proportional to the current in the conductor. The potential difference applied across a conductor is proportional to the current in the conductor. So it is expressed as V is equal to IR mathematically. V is equal to IR, where R is our resistance. So R is the resistance of the material and it is the proportionality constant. So the resistance is independent of the potential difference that was applied to the conductor and the voltage drop across the resistor, and it is also independent of the current in the resistor. It is also independent of the current of the resistor. Now, materials that obey the Ohm's law are said to be ohmic, and materials that do not obey the Ohm's law are non-ohmic. They are non-ohmic. So now let's look at resistivity. The inverse of conductivity is resistivity. So we have rho to be equal to 1 over conductivity. It is the measure of how hard it is for an electric field to establish a current in the conductor. So how difficult it becomes for an electric field in the conductor to establish a current within the conductor, it's termed as the resistivity. So resistivity is proportional to the cross-sectional area of the conductor, but inversely proportional to its length. So mathematically, we can see that resistivity equals resistance times area over length. Now, the SI unit for resistivity is ohmmeter. The SI unit for resistivity is ohmmeter. Now, from Ohm's law, we know that V is equal to IR, and we know our R to be equal to rho times L over A. So we therefore substitute that into V is equal to IR, and you are getting V equals I times rho L over A. But we know that resistivity is equal to 1 over conductivity. So we therefore substitute that into this equation. We're having V is equal to I times the length over the conductivity times the area. So we therefore multiply through by L. So we're having V is equal to V over L to be equal to I over conductivity times the area. But we know that V over L equals electric field E, and I over A equals current density. So after substituting all these into the equation, we're having electric field E to be equal to current density over conductivity. Having electric field to be equal to current density over conductivity. So therefore, this equation proves that current density is equal to conductivity times electric field, as we saw earlier on in the previous slides. So the resistivity of a material is different from the resistance. Resistivity is an inherent property of the material. That is, it depends, or it is unique for every material. And resistance depends on the resistivity and the geometry of the material. So the resistance depends on the geometry and the resistivity of the material. Every material has a characteristic resistivity that depends on its electronic structure and temperature. So resistivity values always depend on temperature and the electronic structure of the material. So we take note of that. Now, internal resistance. Devices like batteries and generators add resistance to the circuit, and this is known as the internal resistance because it is located in the device. In some situations, the internal resistance may be neglected. So internal resistance are like devices that we use in circuit designs, and these devices provide its own resistance. Example is batteries and generators. They provide its own resistance to the circuit, and this resistance is termed to be as the internal resistance. Now we also have terminal voltage. So terminal voltage of a battery is given as change in V is equal to EMF minus current times internal resistance. So when you are looking for, or when you are asked to find terminal voltage of a battery, it is given as the EMF of the battery minus the current times the internal resistance of the battery, and this gives the terminal voltage. Now resistance, the voltage applied to the ends of a conductor is proportional to the current through the conductor, as we saw earlier on in the Ohm's law, and this proportionality is resistance. So we know that resistance is equal to change in V over I. Change in voltage over current gives the resistance. The SI unit is ohms, which is voltage over ampere, and this is the symbol, this is the circuit symbol for resistors. Resistors are used to control the current in the parts of a circuit, so they help in the control of current in the circuit. That's one main use of resistors. Now, ohmic materials. For ohmic devices, the resistance is constant over a wide range of voltages. So their resistance is constant for a wide range of voltage, and the relationship between current and voltage is linear. So the slope is related, therefore, to resistance. So if you look at this graph, as current is increasing, the voltage is also increasing, and it's a linear graph for ohmic devices. And for non-ohmic materials, they have their resistance changing with voltage or current. So their resistance can either change with current or change with voltage, and the relationship is non-linear. So example, we know is a diode. Diode is a non-ohmic material. So if you look at this graph, it is not linear, but it's a curve instead. So their resistance can either be affected by the current or by the change in voltage. So we take note of that. Now let's look at some worked examples. The current density of 1.5 times 10 to the power 5 ampere per meter squared in a cylindrical wire of radius of 1.5 millimeters is uniform throughout the cross section of the wire. What is the current through the wire? What is the current through the wire? So let's look at the solution. So we therefore state our equation for current density. Since in the question we are given just current density and radius, and we're asked to find current, meaning the equation we are using here is current density equals current over area. Now the cross-sectional area of a cylinder is a circle. So the area we take into consideration here is pi r squared. So after doing our change of subject, our current becomes current density times area. So you write out the parameters given in the question, which is current density, then the area. So our current therefore becomes 1.5 times 10 to the power 5 times the area of the circle, which is pi r squared. So we do the substitutions. Therefore, so after computing, we're having current to be equal to 1.06 ampere. Now let's look at another example. Suppose a car battery whose EMF is 12 voltage has an internal resistance of 0.01 ohm. What is the terminal voltage when the current I drawn from the battery is A, 10 amps, then B, 100 amps? So let's look at the solution of this problem too. So firstly, we will state out the equation, which is terminal voltage equals the EMF minus current times internal resistance. So writing out the parameters in the question, we're having our EMF to be 12 voltage and the internal resistance to be 0.01 ohms. So now our first question is, if the current is 10 amps, what will be the terminal voltage? So we substitute parameters into the equation. We have our EMF to be 12, we have our current to be 10, then we have the internal resistance to be 0.01. So after computing, we're having the terminal voltage to be 11.9 volts. When the current is 10 amps, we're having the terminal voltage to be 11.9 ohms. Now, when the current is 100 ohms, we do the substitutions as we did earlier on. So 12 for the EMF, 100 for current, then 0.01 for internal resistance. And therefore, we are having the terminal voltage to be 11 volts. We're having the terminal voltage to be 11 volts. So now here are some trial questions that you can try your hands on.